All right, so today, good morning again, everyone. Today, the plan is to start chapter 3, which is discrete random variables. We are going to introduce the term random variable, the concept of random variables, what are they, and I'm going to solve some examples. We are not going to talk about specific discrete distributions, but I'm going to talk about some general concepts about random variables, the expected value, variance, how do we compute them, what they mean. This is the plan for today. But before we start, we are going to have our first quiz today at 6, and you will have a chance to work on it until tomorrow, 6 p.m. Okay, you will have a day to work on the quiz. The quiz question is going to be very simple, a single question that is similar to what we have solved last week about this diagnostic kit. But in order to have more practice on the Bayes rule and the law of total probability, I will solve some examples from at the end of the chapter 2 today. I picked 217 and 218, but later next week, for example, on Tuesday. By the way, I'm going to post a note to class that my regular office hours for this class will be on Tuesdays, right after our morning class on Tuesday. Okay, so if you have any questions that are from the exercises in the book, I will be happy to answer your questions on Tuesday in my office hour after our morning class at 9:40. But today I'm going to still to practice the Bayes rule more. I'm going to solve some examples from the book. I just picked randomly, actually. I just looked at the exercises where the Bayes rule kind of exercises are, and I think this 217, if I'm not wrong, 217 and 218 seems to be the problems, exercises that are related to using the Bayes rule. Okay, because there's some conditional probability that we are asked in both of the cases. So let's go ahead and start talking about this. By the way, let me change my mouse pointer size to 4. All right. Okay, so let's start with this one, exercise 2.17. And I'm going to again write on the whiteboard what we are given and what is the probability that we are asked. So here it seems like there are three different things. So let's read the statements. A computer assembling company receives 24% of the parts from supplier X, 36% of the parts supplier Y, and the remaining 40% of the parts from supplier Z. So we can actually denote these events. For example, the event X may be the event that tells that the supplier is from the supplier X. So the probability of X is 0.24, probability of Y, the probability that this is from supplier Y is 36%. If you add those up, you're going to see they add up to 100%. So this is the first thing we're going to get from the first sentence is that these are exhaustive. Part can either come from X, Y, or Z. These are mutually exclusive and exhaustive events. So let's write these. So what I know is that the probability of X to happen is that X denotes the events where the part comes from supplier X is 0.24. Right, let me check them again. 36 from Y, 40 from Z. So probability of the supplier coming from Y is 0.36, and probability that this event Z happens, in which denotes the outcome that the parts are coming from supplier Z is 0.4. Now, what are we asked? 5% of parts supplied by X and 10% of parts supplied by Y and 6% of parts supplied by Z are defective. All right, so how are we going to make use of this sentence? This is actually doesn't seem like a directly conditional probability, but it's conditional probability is given to us here. Basically, let's denote the event where a part is defective as PD. Okay, so PD is the probability that a part will be defective. Now, when we are given the statement that 5% of parts supplied by X, 10 and then 6, 5, 10, 6. 5% of the parts supplied by X are defective. It means that if the supplier is defective, the supplier is X. If you're given that the supplier is X, the probability that the part is going to be defective is 5. So we are given this conditional probability. Probability that the part is defective, given that the supplier is Y, is 10. And the probability that when the supplier, when we know that the event Z has occurred, the part comes from supplier Z, the probability that it's going to be defective is 0.05, 0. So let me actually just erase these parts, and yeah, I can actually just select or just directly erase them here. Yeah, let me increase the size. Oops, it's too much. Yeah, this is better. All right, yeah. Let's get back to this. Reduce the size to 4. Opacity. Okay, now it's 0.05, 0.10, 0.06. Okay, so we are also given this. We are given these conditional probabilities. This is not given to us right now, but you'll be able to find that probably. And these unconditional probabilities are given to us. Now, we are asked, if an assembled computer has a defective part in it, what is the probability that this part was received from supplier Z? So now we are asked here, what is the probability? We are asked this conditional probability. If we have a defective part, what is the probability that given that a part is defective, what is the probability that it comes from supplier Z? So, okay, so we are asked this. As you can see, all the conditional probabilities that we are given are of this type. The suppliers are known, defects are not known, but we are asked this probability. Now, this is a direct application of the Bayes rule. What we need to do is we are asked what is the problem. So when we write the Bayes rule, it will be equal to this probability of Z divided by probability of D, right? So this is the Bayes rule. So both of these left-hand side and right-hand side they denote the event. What is the probability that the event is defective and the part comes from supplier Z? Okay, so these are, if you put this D here, PZ given D times PD is the intersection of these two events, PZ and PD. Now, and the same is this true for the right hand side, and we are not making use of any independence assumptions or anything. Okay, so this is just basically the conditional definition of the conditional probability. The intersection events on both sides are written in two different ways, and this gives us the Bayes rule. Now, this one is known. This is 0.06. We know what PZ is, 0.4, but PD is not given. So this question is also a direct application of law of total probability. In order to find PD, I'm going to make use of. So there are three mutually exclusive and exhaustive events, which are this X, Y, and Z. So if I find the intersection of X with D, Y with D, and Z with D. So if we were given the intersection of X and the events X and D, Y and D, and Z and D, since these are X, Y, Z are mutually exclusive and they are exhaustive events, the summation of these intersections would give me the unconditional probability of PD. So in other words, this lower hand part could be written as, okay, it first comes from this X and D plus probability of Y and D plus the probability of Z and D. Okay, so this is, you understand this part, I hope. So the intersection of these three intersecting regions, they are mutually exclusive. So I can add them directly without subtracting anything from them. And since they're exhaustive, X, Y, Z, these events are exhaustive, they're actually going to cover the entire D, the event D. And therefore, this is the total probability I have for the unconditional probability is going to be this. So how can I find these intersections? They're also not given. These intersections I can find by making use of the conditional probability rule. Px and D is simply Pd given X and Px. I'm going to use the conditional probability that are given to us. So Pd given X and multiplied by Px gives me this probability, okay, the intersection. Because I know that the conditional probability is defined as the ratio of the intersection over the event Px. So if I multiply these two things, I get the intersection. So all you need to do is multiply these, D given Y times Py, the unconditional probability Pi, and plus Pd given Z plus Pz. Okay? Now, in all of these cases, you see that you're adding three things, and one of these things that we add is actually in the numerator. So we are asked like this is like we're finding the probability. It's like a weighted average of, or the weight of Z of our beliefs. So these are our different beliefs that this and this event occurred together, this event and this event occurred together, this event and this event occurred together. So when we add all those up, that's exhaustively occupies all of our belief. And the ratio of the question that we are asked, what is the probability that the part comes from supplier Z, is actually one of these three things as a ratio of this summation. Okay, so again, this is just an intuitive thing maybe that helps you understand what's going on if you forget the formula or if you forget the Bayes rule. Okay, now all you need to do is make this multiplications. Everything here is given in the question. So this is 0.06, this is 0.4. I'm going to also have them here times 0.4. And D given Y here 0.10, Py 0.36, D given X 0.05, Px 0.24. You add these up and you divide this by this addition, summation, and you're going to get the result. Okay, so this is exercise 2.17. Any questions from this exercise? So it basically focuses on the law of total probability and application of the Bayes rule. Now, if you go and take a look at what exercise 2.17 is about, it's about quiz. A multiple choice quiz is answered correctly with probability 0.9 if a student is prepared. Now, again, let's define two events. The event that the question is answered correctly, let's call it event C. The question is answered correctly. And event S, let's S denote the event that the student has prepared for the quiz. Okay, so there are two things here. If a student is prepared, we are focusing on a specific problem on this multiple choice quiz. The probability that the question is going to be answered correctly, let's denote that event with C. All right, now what we are given here is that if a student studies for the exam, the probability of that is being answered correctly is 0.9. So we are given this conditional probability. And the other sentence saying that an unprepared student guesses between 4 possible answers randomly. So the probability of choosing the right answer is 1/4. So that when the student is not prepared, which is that we are given this conditional probability, in the case of not studied, we have 0.25. Okay, so these are the conditional probabilities. Now, these conditional probabilities also tells us, for example, the probability of not answering correctly when a student is prepared is 0.1. Okay, so the left-hand side, when you take the complement, you get the complement event, which is 1 minus 0.1, and also the probability that it's not answered correctly when a student is not prepared is going to be 0.75. Okay, so the first two sentences gives us these probabilities. Now, 75% of students prepare for the quiz. So what does this tell us? The unconditional probability of studying for the quiz, so which is 0.75, which means that 25% of the students do not study for the quiz. So this is the unconditional probability of preparing for the quiz. If Mr. X gives a correct answer to this, so one of the students, if Mr. X, if he gives a correct answer to this problem, what is the chance that he did not prepare for the quiz? Okay. So we're asked the probability that, what is the probability of not preparing for the quiz when that Mr. X gave a correct answer to the question? So given that the problem is answered correctly, what is the probability that the student has not studied for the quiz? Okay, so this is the probability that we're asked. Again, if we apply the Bayes rule for that, because all the conditional probabilities that we're given here, if you look at the question, the given thing is the having studied or not. Okay, so the conditioning is on the study event. But now we're asked the question because we observe something that is the final outcome of the quiz, and we try to predict something. If we see that the question is answered correctly, what is the probability that the student is not prepared? So we are asking some different conditioning. And these types of questions, after I solve this, I'm going to show its relationship to machine learning applications. So the Bayes rule, especially the utilization of Bayesian networks, which shows which features are independent from each other or have some cause-effect relationships between them, those networks, actually gives us conditional probabilities and helps us predict certain machine learning tasks. And I'm going to also talk about the relationship of this Bayes rule to machine learning. But let's first focus on this question. If I directly apply the Bayes rule, what I have is this divided by probability of giving correct. Okay, so this is S complement. So I basically, what I did was, again, this is the I'm interested in the intersection of S complement and having correct answer. So this part, this one, multiplied with this gives me that intersection event. This right-hand part gives me the same intersection event, the probability of answering correctly and not studying for the final exam. So this is that intersection event. But we are interested in not the intersection. We are already given that the answer is correct. Okay, this information is already known. Now, what is the probability that the student did not prepare? If we look at this question, what is given to us? This one is given to us. This is one of the probabilities I have written. The probability that answering correctly given that the student did not study. This is 0.25. The probability of not studying for the exam is 0.252. So both of them on the numerator, 0.25, 0.25. This is not given to us. What is the probability of answering correctly unconditionally we don't know whether the student has studied or not. Again, when we apply the law of total probability, This can be written as probability of answering correctly when studied, when the student studies, plus the probability of answering correctly when in the case of when the student does not study. So the study and not study are mutually exclusive and exhaustive events again. And if so this one is written as a summation of these two probabilities. Again, one of these probabilities, you see, this one is the exact same thing as the numerator here. And the other that we add up is the other case where the conditional probability where the student studies. So everything, as you can see, is given 0.75 times 0.9. So this one is 0.9 times 0.75. And the other is 0.25, 0.25. And the one on the numerator is also 0.25, 0.25. So you just do the math with your calculator and you get the answer. All right. So in machine learning, we usually have things like, by the way, do you have any questions about this exercise 2.18? Both of them are straightforward application of the Bayes rule with the utilization of law of total probability. If you solve the other exercises, it will help you understand to apply this rule when questions like these appear. All right, so in machine learning, we usually try to, one of the problems in machine learning is classifying objects. For example, you may have an image, okay, and there may be something in this image, an object classification, for example. I'm not an image processing or computer vision person, but I know that this is one of the classical problems in machine learning, and many deep learning algorithms actually do this object recognition now these days better than humans. But if you look at this problem, there's an object in the image, and we try to identify, for example, whether is a, so it looks like a seal on an iceberg. Okay, so is this animal a seal? Let me put the whiskers and it will look more like a seal. So I have this animal on this image. Now I want to figure out, I want to automatically classify the species. Is this a polar bear? Is this a seal, or is this something else? So what we usually do is, so in this machine learning task, the final prediction is usually a prediction with certain confidence. So we are actually asked this conditional probability most of the time. What is the probability that it's going to be the seal event is going to occur? Or what is the probability that the bear event is going to occur? Or what is the probability that it's going to be an iceberg? Or what is the probability? So we may have different objects that we want to classify into a tree. Okay, so usually we are trying to find this probability given certain things. What are these given certain things in the image? These are multiple things most of the times. So this conditioning, whatever we are conditioning, may be actually multiple events. For example, the event that these are the things really easily to compute, what we call sometimes features. Okay, so these are features like, for example, the color. Given that the color is white, for example, what is the probability that it's a seal? What is the probability that it's a bear, polar bear? Or so this is something given. Or the probability that the width over, so I have this animal and I measure its width over height, for example, given its width over height from this image, or given certain textures on the image. So after we first process this image, we extract features like this, which are the things that are given in the image. So observing this, we try to then figure out this probability, that what is the probability that it's seal, bear, or this, okay? So on our training usually is composed of, for example, how many of the seals have some white fur, or how many of them have black fur. So in other words, our training data is of this type. Given that it's a seal, we have some data, training data, gold standards When we measure things like we know that this is a seal image, and for example, the probability of being white, for example, 75% of the polar seals in Arctic Circle is, for example, they're white. 25 of them are brown. So these are our training and our model. We observe these things, and after that, for example, what is the rarity of a polar bear when you take a random image? What is the unconditional probability of it's becoming a seal or a polar bear or an iceberg? And with that, some of these features may be related to each other. Okay, they may not be independent. Usually, this is what Bayesian networks show us, the relationships between those things. And it's really sometimes when you have many features, it may be much more difficult to compute the joint probability distributions, which we are going to talk about in chapter 3, to hopefully today. But this is basically a direct application of the Bayes rule also in machine learning. We are given some model which is conditioned on known things, knowing that we have a seal, we know the occurrence of the probabilities of these features. Then when we observe these features, we try to predict the outcome, the output variable. In this case, it becomes the type of the animal that we don't know from an image. Okay, so there are some methods that actually apply this Bayes rule to answer questions like these. All right. Before I move on to chapter 3, do you have any questions? So this ends the chapter 2. Okay, now I'm going to move on to chapter 3, which we are going to, yeah. Oh, so this is when you're confused between these two things, the right-hand part it means that it's given. So this one is the right-hand part. So this probability, you should always read this probability it's like you try to read these conditional probabilities from right to left. So given that the seal event has occurred, meaning that given that this object in the figure, I know that it's a seal, then just imagine that you are not able to observe, you don't see the image. So if I give you a seal image, what is the probability that it will be white? White is not something you observe. You don't have the image actually. When you have the image, it means that you have all these features. This is like knowing from the object side if how many percentage of the seals are white. This is that probability. So if you try to read it from right and treat this right-hand part of this pipe as the thing that is certain. Okay, so this is given this event has occurred. So this right-hand part restricts our sample space to only seals. Okay, to only bears if it's right on the right-hand side. So given that for certainly this event has been observed, given that we have a seal, this left-hand part becomes the uncertain, the probabilistic part. What is the probability of observing? It's white. Okay, so it may be confusing if you already have the image. This probability, if you already have a single image, this probability doesn't make sense because on the image you see a seal and it's white or brown. Okay, so it's going to be actually when you see the image, it's going to be a specific outcome that you're observing. Therefore, you will not be talking about probabilities like this. Okay, when you're talking about a probability like this, it means that you don't know whether it's white or black or so this is the event that you're looking for, the probability. This is the uncertain part. This right-hand side part is the part that is given to you as the event that has occurred. So I hope it's clear. Any other questions you may have from chapter 2? Okay, now I'm moving to chapter 3, in which we are going to associate these events. Some events are, each outcome actually is going to be associated with a number. Now, up to now, when we are talking about events, for example, even in this question, for example, I was saying, px. The events we just use, for each event we use a capital letter to indicate the entire set of outcomes that belong to this set, this event. So events are really abstract. They're subsets. An event is basically a subset of the sample space, so it's a set of outcomes. They are just sets at this moment. Now, in order to study these probabilities in a better way, quantitatively talk about things, for example, expected outcomes and distributions, one thing we may need to do is we may need to have a mapping between these outcomes and numbers. This is what a random variable is. So let's first define what this is. Here's the first time maybe you hear the concept of this random variable. A random variable, just like the event names that we use, x, y, z. Now, a random variable, on the other hand, is not a subset. A random variable is a function of from the domain is the sample space, okay? But you know what from mathematics, you know what a function is, right? For example, a function f from domain, some domain to another from a range. So this is, for example, fx is equal to, when you say fx is equal to y, all the possible values you can put into this function as input is called the domain of this function. And the outcome of this function, its results, are called the range of this function. So now, a random variable, the random variable itself, is a function in which the domain is the sample space, which means that when the domain is the sample space, the input we give to a random variable is a single outcome. Okay, so the elements of this sample space, which are individual outcomes, are given to this function, which we call random variable, and the output is any numerical number. It may be a continuous number like real numbers, it may be integers, it may be anything from minus infinity to plus infinity. Okay, it may be just 0 and 1. Okay, so this is a random variable which is a mapping which maps outcomes to 0 and 1 only. It's a random variable. We are going to see that this specific random variable is a discrete random variable in which the range is countable, or it may be infinite, but it's still countably. So if we can count it like the set of integers, maybe discrete, or we may also sometimes treat them continuous. So the continuous and discrete, the distinction between them is not exactly black and white. We're going to come to that later, but let's first focus on this concept of random variable. Okay, so it's a real or integer valued function. So it says that its ranges, it just maps an outcome to some number. Okay, I'm giving you so this is really an abstract definition, and it's going to be clear very shortly. Which is like, for example, look at, we have talked about the event where we tossed 3 coins, right? 3 coins. The outcomes were like head, tail, tail, head, tail. So there were 8 possible different outcomes. Our sample space contained 8 outcomes. Now, a random variable, you may define a random variable something like this. The random variable is the number of heads. When you toss a coin 3 times, the number of heads is my random variable. So when you get any outcome, you immediately count how many heads are there, and this is your mapping. Each outcome is uniquely mapped because it's a function. Every outcome is uniquely mapped to a number. An outcome cannot be both 1 and 0 at the same time. When you look at the specific outcome, for example, head, tail, head, what is the result? 2. Head, head, what is the value of the random variable? 3. Tail, tail, what is the value of the random variable? 0. So when you toss the coin 3 times, and when you define this random variable as the number of heads in my 3 coin tosses, then this random variable, it can get 0, 1, 2, or 3. these are the 4 possible values our random variable can get. But as you can see, they're all numbers. They're something numerical. That's what a random variable is. When we define a random variable, it can, that function, for any outcome in the sample space, it will convert it, it will generate a number. It will result in a number. So this definition, this concept of random variables allows us to study interesting things we are going to see the remainder of this chapter and also the next chapter too. So, and similar to events, we denote random variables by uppercase letters, and we will denote probabilities like this. So, for example, when x is a random variable, we will, for example, the probability that x is equal to 3, if that x is the random variable, number of heads in 3 coin tosses. Okay, so this is the random variable we define, and this will be the event where the number of heads is equal to 3. So this is we are going to denote events like this. When we say px, this doesn't specify a particular event actually. We will not be able to use random variables like this. Probability of there is no, I mean, we need to associate, in order to talk about probabilities, we need to, the random variable itself does not directly indicate an event. The random variable is just that mapping. But when you say the probability being equal to this particular value, this denotes an event. And this is, for example, another event. This is another event. And these events, if these are all the values my random variable can take, 0, 1, 2, 3, as you can see, these are all mutually exclusive events. For example, an outcome, if you look at the intersection of these events, can an outcome be mapped to both 0 and 3? No. There is a unique mapping from an outcome to a number. So the intersection of these events are empty sets. So they are mutually exclusive. And they're also exhaustive if these are all the possible values that my random variable can take. All right, so let's look at more examples. So the corresponding value, sometimes if we use it as a variable, we use this lowercase letter like this to indicate a probability. We can also define events not only with equality. For example, what is the probability that x is less than or equal to 2? We can, since these are numbers, x is a random variable which is a number, we can ask probabilities not only involve equalities like this. This is also an event. Look at this event. What is this event? This event actually is the union of x is equal to 0 or x is equal to 1 or x is equal to 2. Since these are exhaustive events, I can actually add them up like this. Plus x is equal to 2, right? They are exhaustive events, and I can therefore add these events. And I can ask probabilities also. What is the probability that x is greater than 2? Which is, this will be the same as this one in this particular example. But we can ask inequalities like this, less than or equal to type of things, or less than 2. For example, the probability that x is less than 2 is not going to contain this one. All right, so it's just going to contain the event where x is equal to 0 and x is equal to 1, and the number of, in this event where we have, in this experiment where we have 3 coin tosses, and we may define the random variable as the number of heads. We can define different random variables numerically in different cases. Here, for example, pick a random student from our department and let x be the age of the student. Okay, so this is a random variable because it's numerical, any outcome. So I pick a random student. When it's greater than 2, shouldn't we include from 3 to infinity? Actually, 3 to infinity is already included here. So let's look at this question. When the probability, so when the probability is x is greater than equal to 2, we should include infinity, but the possible values x could take is only 0, 1, 2, 3. For example, this one, the probability of x is equal to 4 is 0. The probability of x is equal to 5 is 0. The probability any integers all the way to infinity, that's these events have 0 probabilities. So when you you can include all of the things after 3, add up all the probabilities, but since you will be adding all zeros, it will not change after 3. So this for a discrete event like this, okay, so this is a discrete random variable, the probability function is not going to change from all the way to infinity after 3. Similarly, it's going to remain 0 all the way starting from -1, for example. It will remain like that. So the values that it can take is clearly important, all right? So it will define where it will tell us where to stop our computations, where should I continue further, and from this on forward, for example, what happens between minus infinity and infinity, it will tell us what happens. And especially in discrete variables like this, we don't think about infinities that much, because we need to have usually we are bounded by some limit, and what we're doing is we use summations to indicate these probabilities when we have discrete variables. When we have continuous random variables, we are going to talk about that later. It may be confusing right now for you, because continuous random variables, the random variable can take any value, uncountably many, between two numbers, maybe finite, but uncountable. It's still going to be continuous. In that case, for example, a probability like this, the probability that x is equal to a particular specific number, that probability is going to be 0 for any cases, even if it's something possible. A continuous random variable is like the lifetime of a light bulb. For example, observe the lifetime of a light bulb, lifetime in minutes. Minutes seems like an integer value, but for example, if you allow them to be represented, for example, 13.18 minutes, if you also allow the decimal point to have it in a real number, if you're measuring seconds and milliseconds, that will be a continuous random variable. And in that case, for example, what is the probability that the lifetime of a light bulb is exactly 3 minutes? That exactly 3 minutes will be a point in that continuous region. And that point is going to be one point among infinitely many possible outcomes. Therefore, that single probability is going to be 0 for continuous random variables. In that case, so why do we study continuous random variables? We usually will ask things. We will not ask questions when we have a continuous random variable. We are not asking questions like, what is the probability that the lifetime of a light bulb is 3? Why are we interested in exactly being 3? For example, we ask questions, what is the probability that the lifetime of that light bulb is between 3 and 4 days? Or it's more than 4 days? What is the probability that it's going to last more than 4 days? So we'll be asking probabilities of ranges, the random variable, the ranges of values the random variable can take, and they will be non-zero. Okay, so point probabilities for continuous random variables, they will be 0, but the probability of a range will be non-zero. So we will talk about, chapter 3 and the second part of chapter 3 talks about discrete random variables in more detail. And chapter 4, we are going to talk about continuous random variables and some known, very widely used family of distributions. So there are, for certain problems practical problems that we face in real life, the distribution of that type of random variables has been studied a lot, and people have seen that they follow certain specific patterns, and certain specific formulas are applicable for these types of discrete random variables, like, for example, arrival times of buses at a bus stop, number of successes in certain trials where the number of success in a single trial is a certain probability. So we'll be able to measure some of those with mathematical functions. We will be able to compute the probabilities of individual outcomes, and then we will ask questions, for example, like when I do this experiment, what is the expected value of that random variable? For example, we can ask the question, for example, let's x be this random variable, the age of a student uh, from our department. For example, if I pick you maybe ask questions like, for example, if I pick a random student, what would I expect X to look like? Is it going to be around 20s? For example, if somebody tells me that the expected age of the student is 55, I will be really surprised. Or if somebody says I picked a student and the age is 55, I will be surprised. Why would I be surprised? Because in that case, we have certain expectations about this value of this random variable. Like on the average, what is the age of a student? This average number will give me an idea about some global feature about this random variable and how variable are the ages in this department. For example, if the average may be both 20 in two different departments, but it may be the case that in one department half of the students are age 10 and half of them age 30, it's still 20. The average is still 20, but it's really something very different than a regular college, right? I mean, where we expect all the students to be around 20 years old. But if you have this weird college, let's call it, which has students of 10 years and also students 30 years, its expected will also be 20, but there will be something different between these two colleges, right? The variance, how each outcome differs from this expected value. The average difference, like which we call the standard deviation, also tells us something about that random variable, and this is what we are going to also learn how to compute in this chapter. So yeah, I already mentioned some of these things here, random variables and probabilities. A certain event here, each value of a random variable is an event, like px is equal to, so this is the same example that I gave on my whiteboard. 3 coin tosses example where x is the number of heads. Each value of a random variable is an event. We may compute probabilities of these events. What is the probability that x is equal to 2? There are three outcomes which are mapped to random variable value 2. And since if we have a fair coin, each of these outcomes will be equally likely, which means they have the probability 1 over 8, 1 over 8, 1 over 8. Outcomes by themselves, they are mutually exclusive, so we may add these probabilities to find the probability of an event like this. And here, when we analyze these things, if you look at all the probabilities for all the values of a random variable can take, in the case of discrete random variables, so we call this a discrete random variable if the values that this random variable can take is finite or countably infinite, then the RV is discrete. Actually, in the second case, when we have like the integers, for certain problems, modeling a random variable which can take a lot of integers can be modeled with a discrete distribution as a discrete random variable. But sometimes we may also model this if the number of values this random variable can take is on the order of thousands, millions. Maybe modeling it as a continuous random variable may make more sense, because the equations, the probability functions that we use for these discrete variables, they will be very difficult to compute when the summation is too long. Okay, actually you'll see that, for example, in certain cases when the number of values we take is more than 30, for example, there are approximations, continuous approximations to these discrete random variables, which we most practically use most of the time. So the second part is open to discussion, actually. When you have countably infinite variables, do you really call it discrete random variable? Because if you do that, philosophically, everything is discrete, right? I mean, even if you're measuring the lifetime of a light bulb, at some point you're going to say, I'm going to accept only 6 digits after the decimal point, which means that even if you have real numbers, I mean, the precision, if the precision is limited, everything is going to be discrete. Exactly 3 years is 0 because so here for the case of the light bulb, the variable itself was continuous. Okay, so 3.0001 was possible, 3.1023 was possible. So since it's not a discrete variable, therefore for that light bulb we cannot talk about discrete values. We are in a real domain in that case. Okay, but what you're thinking is right. Since all of the values in that small area, and there are uncountably many different values when you are considering continuous random variables, to be that that single point, and the area under that single point, the area of that curve under the single point is going to be 0 because that's a single line. A line does not have any area, it's 0. That's the reason the probability of the exact point probabilities will be 0 in the case of continuous variables, because there are infinitely many outcomes. If each of them are equally likely, it's 1 over infinity. Okay, it's actually that if they are all equally likely, that will be 1 over infinity, and that 1 over infinity gets you 0. And that's the reason we are choosing a range. You're correct. Now, but in the case of this, now let's forget about continuous random variables. In this chapter, we are going to focus on discrete random variables. And if we look at the function, if we are able to calculate the probability for each individual value the discrete variable can take, for every value of x, and we just collect these as a function, this is called the probability mass function of a discrete random variable. And it's indicated by this lowercase letter f, which is subscripted sometimes by the random variable label. So this probability mass function is directly gives us the probability. So we get the individual value of the domain of this is the values the random variable can take. For example, we can just give 0, 1, 2, 3 to this one. Remember, the domain, the random variable itself, its domain was the outcomes, the set of outcomes, the sample space. Now, this is just considering the same thing. The probability of x is equal to x. Just if we have a function which is called the probability mass function, which we compute for all possible values x can take, we can then ask probabilities by using this lowercase f, saying that what's the probability that x, this random variable x, is equal to this particular x. So it's like what we will be asking things like this. And after that, I'm going to have a break. For example, what is this? What is f3? In the case of this 3 coin tosses, f3 is going to be 1 over 8. What is f2? Okay, it's going to be 3 over 8. What is f1? It's also going to be 3 over 8. What is f0? It's going to be 1 over 8. So these are the possible values our random variable can take, 0, 1, 2, and this lowercase f, which we call the probability mass function. Probability mass function in the case of discrete random variables gives us the probabilities directly. In the case of continuous random variables, this function f will have a counterpart in the continuous case, which is called the probability density function. And it will not give us directly the probabilities. Okay, the probability density function For example, it will have a non-zero value. The probability density function, for example, when you in a continuous, in the light bulb example, for example, F3 may be 0.2. Okay, this doesn't mean that the lifetime of a light bulb to become 3 is 0.2. This function, which we call the probability density function in the case of continuous random variables, it will not show us the probability. Okay, so this is really, this is like a heads up warning beforehand. This small function f does not always show the probability. In the continuous case, we are going to integrate this f, fx dx, from, for example, 3 to 4 to figure out what is the probability that the lifetime of the light bulb is between 3 and 4 years. Okay, so this function, we will use it to integrate. So it may have a certain point on this curve of this function will have a non-zero value, but this will not be a probability, not probability. Okay, so in the case of continuous random variables, when we have a probability density function. But in the case of discrete random variables, these are true. They are probabilities. The probability mass function is defined as the probability that x is equal to x. And yeah, let's have a break now for 10 minutes. And after the break, I'm going to describe another function which we call the cumulative distribution function, which will be defined as the probability that events inclusive from minus infinity to a certain value of that random variable. All right. Now, yeah, I'm going to stop recording.